Now, as a way of introduction to this video, if we were to have a tennis ball to weigh using 3 different weighing devices, would we have the same readings on these devices? So for example, if we have an ordinary bathroom scale, now the scale that we usually have in our bathrooms, a laboratory balance, and an expensive analytical balance, usually the one used in clinical and research laboratories, are we going to have the same readings on these 3 devices? Now for a tennis ball, the bathroom scale may weigh 0 grams. Now the same tennis ball is placed on a laboratory balance and it weighed 56.07 grams. And on the analytical balance, we had 56.07138 grams. But why are the readings different for the same object on different measuring devices? Now, it is important to note that for every experimental measurement, no matter how precise, has a degree of uncertainty to it, because there is a limit to the number of digits a device can determine. So how do we deal with this limitation? Uncertainty in measurement takes care of this limitation. But how does it work? Now, for values recorded, as in this case, we make use of all the digits that are known with certainty, plus 1 additional digit usually considered uncertain. So for this particular reading, 5, 6, 0 are considered certain, but 7, which is the last digit, is considered to be uncertain. Now let me use an ordinary measuring cylinder to explain what I mean by certain digits and uncertain digits. Now if we are to consider a simple device with such calibration, certain values are very certain. We are certain of 5, 10, 15. We are certain that the smallest unit for this calibration is 1 centimeter. But what if we have a value here in between the smallest digits to estimate? So is this 7.5, or is it 7.6, or is it 7.4? So the digit 7 is very certain, but the last digit, we are not too certain about that. And so to avoid this uncertainty, we factor in this uncertainty in measurement by plus or minus 1. It so applies to these measured values. So we make use of all the digits that are known with certainty, plus 1 additional estimated value, which is usually considered to be uncertain and which is usually the last digit. And so we treat the last digit by plus or minus 1. So the exact value of this measured value is between 56.08 grams and 56.06 grams. And so here we're considering the uncertainty in measurement as plus or minus 0.01 grams. And for this measured value, the exact value lies between 56.07139 grams and 56.7 grams. And here our uncertainty in measurement is plus or minus 0. grams. So now the recorded value, in taking into account the uncertainty in measurement, will now be written as and this recorded value would be written as Now, with most of our digital instruments, they do not come with graduations. And so it becomes very difficult to determine the smallest increment on them. And so to factor in our uncertainty in measurement, we consider the last digit as the uncertain digit. And we apply our plus or minus 1 to our last digit. So this is just an example to explain the values that are known with certainty and the one which is uncertain, which is usually the last digit, that has to be estimated. But how do we determine the plus or minus value to use? Now, let's look at this example. Now, we have a measuring cylinder over here that has been calibrated in intervals of 10 using the big lines. Now, in between the big lines, we have smaller lines. So the measuring cylinder has subgraduations. Now, we can manually count the subgraduations. So if this is 10, We have 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have smaller increments of 1 milliliter. So we can do the manual counting, but we can also use this option. The difference between the big lines so this 10 millimeter has been subgraduated into 10. So the smallest increment on this measuring device is 1 milliliter. Now, what reading are we going to have for this? Now, we're going to take our reading from the bottom of the meniscus, which lies somewhere between 15 milliliters and 16 milliliters, but closer to the 15 than to the 16 milliliter mark. So I'm going to estimate my reading to 15.3 milliliters. However, if we are to have different people doing this recording, different values would be the case. Of course, 15 is certain, but the number to be estimated may be different. So how do we determine our plus or minus value? So for our uncertainty, we make use of our smallest increment and we divide by 5, which is going to give us plus or minus 0.2 milliliters. With this, we're going to record our reading in this form. Which would then mean that if 2 or more people are to take the recording of this level, any value that falls between 15.5 milliliters and 15.1 milliliters would be acceptable for this range of values of the volume. Now, let's take a look at this second example, showing a graduated device where the big lines in intervals of 2, and we have smaller graduations of 10. So we have So to determine our smallest increment, we're going to divide 2 milliliters by 10. And our smallest increment is going to be 0.2 milliliters. Now, if we want to do the calculation manually, this will be, we have 4 here. So this will be 4.2, 4.4, 4.6, 4.8. This will be 5, 5.2, 5.4, 5.6, 5.8, and 6. So 0.2 milliliters is our smallest increment. So what is going to be this reading? Don't forget that we take the reading from the bottom of the meniscus. Now, our dotted line is between the 4.8 and the 5 milliliter mark, but it is closer to the 4.8 than to the 5 liter mark. So I'm going to record this as 4.83 milliliters. So with this recorded value, we're going to introduce our uncertainty in measurement. We would need the smallest increment on our measuring cylinder, and we divide it by 5. So if our uncertainty is to be factored into our recording, we're going to have now with this recording, it means when 2 or more people take the same reading, we have the possibility of having a range of readings between 4.8 and 4.79 milliliters. So this range of figures takes into account human error, and it also takes into account imperfection and limitations that all devices have. We should also take note that our recorded value should have the same number of decimal places as our uncertainty in measurement. If our uncertainty in measurement is to 2 decimal places, we should keep the recorded value also at 2 decimal places. So the uncertainty is not 0.2 milliliters because I can easily identify those small lines. So for the uncertainty, we need to go beyond that and divide by 5. But how do we arrive at our number 5 that we use to divide? Well, in some books, they don't divide by 5. In some books, they divide by 2. And some people even go to the extent of dividing by 10. So even within the science community, there is some disagreement as to the number to use to divide. However, I would suggest that in your college class, you may want to check out for the number that is being used in the class, because there is disagreement as to what number to use. So by this recording, it would mean that when you read it and I read it, the value might not be the same, but they should be within 0.04 milliliters. So this is the end of my video. Thank you very much for watching, but keep watching.